Hello there, and welcome to Sleepy Science Vault. Water is one of the oldest travelers on Earth. Long before mountains had their current shapes, before the first forests spread across the land, before anything walked or swam or breathed, water was already moving. Rising, falling, gathering, and rising again. The cycle you are part of tonight has been running without interruption for roughly 4 billion years. That is not a number the mind can truly hold. But consider this, the water in your body right now has been on this planet since before complex life existed. It has passed through ancient seas, through ice ages, through the clouds of prehistoric storms. It belongs to a system so old, so perfectly closed, that not a single drop has ever truly been lost. We know this partly because of something remarkable preserved in stone. In rock formations dating back 2.7 billion years, scientists have found the delicate imprints of individual raindrops, tiny craters pressed into ancient sediment and held there across unimaginable spans of time. Those drops fell on a world almost unrecognizable to us. No grass. No trees. A sky with a different color. And yet the physics of that falling water was identical to the rain that touches your window on a quiet evening. The water cycle is, in the truest sense, a closed system. Water does not escape into space. It does not disappear. It transforms, from liquid to vapor to ice and back again, but it remains here, circling endlessly within the thin, delicate layer of atmosphere and ocean and land that wraps around our planet. This is why something so quietly astonishing is scientifically possible. The water that fell as rain on the back of a living dinosaur may, quite literally, fall on you today. It may have been locked in a glacier for 1 million years before that. It may have drifted over continents as vapor, invisible and weightless, before condensing into a cloud above the place where you now rest. And yet for all of water's abundance on Earth, all those vast oceans stretching horizon to horizon, only about 1% of it is accessible to human life. The rest is locked in ice, buried deep underground, or held in the salt of the sea. That one thin slice of available water sustains every river, every well, every glass of water ever poured. The entire thread of human civilization runs through it. A single raindrop's journey through this system might be brief, a matter of days, moving quickly from ocean to cloud to river to sea again. Or it might be extraordinarily long. A drop that soaks into certain deep aquifers may rest there for thousands of years before it moves again. There is no single timeline. The journey is shaped by temperature, by humidity, by the slow drift of climate, and increasingly, by the choices human activity makes. We have become, without always realizing it, a force within the water cycle itself. The path of a raindrop is also shaped by forces far larger than any single storm. Global wind patterns carry moisture across hemispheres. Ocean currents redistribute warmth in ways that determine where rain is plentiful and where the earth runs dry. The arrangement of continents and mountain ranges guides the movement of clouds as surely as walls guide the movement of water in a channel. Every raindrop that forms is already embedded in a system of vast, interlocking influences, some planetary, some atmospheric, some traceable back to the geometry of Earth's tilt toward the sun. And here is something worth sitting with quietly. The water that soaks into the ground where you live today may one day evaporate, drift on the wind, and fall as rain in another country entirely, on a hillside, in a forest, in a city you will never visit. Water carries no borders with it. It passes through all of them. Every journey has to begin somewhere, and for a raindrop, the beginning is evaporation. It starts not with falling, but with rising, with warmth touching the surface of water and coaxing individual molecules gently upward, away from rivers and oceans and lakes and leaves, lifting them silently into the air. It is, in its own way, a kind of departure, the first quiet step of one of the longest journeys on Earth. Evaporation draws water upward from the obvious places, the open ocean, the surface of a lake, the wet earth after rain. But water also enters the air through a quieter, more intimate process happening all around us, in every forest and field and garden. Plants breathe water out. Through microscopic pores in their leaves, trees and grasses and crops release water vapor into the surrounding air in a process called transpiration. A single mature tree can release hundreds of liters of water into the atmosphere on a warm day. Multiply that across a forest, across the Amazon, across the boreal forests of the north, across every green and living landscape on the planet, and the contribution becomes immense. A significant portion of the rain that falls over land originates not from the ocean, but from the land itself, exhaled by the vegetation growing on it. Forests, in a very real sense, help generate their own rainfall. They are not just passengers in the water cycle. They are participants. All of this water, evaporated from oceans, lifted from rivers, exhaled by leaves, enters the atmosphere as invisible vapor. And as it rises, it moves into a different world. The higher you go above the Earth's surface, the colder the air becomes. With each kilometer of altitude, the temperature drops. And as warm, moisture-laden air rises and cools, something begins to shift. The vapor starts to look for a way to become something more solid, more defined. It reaches a point where the air simply cannot hold it in its invisible form any longer. But water vapor does not condense into droplets on its own. It needs something to gather around. This is one of the subtler, more surprising truths about how clouds are made. Floating through the lower atmosphere at any given moment are countless tiny particles, specks of dust lifted from dry land, pollen released by flowering plants, microscopic fragments of sea salt thrown into the air by breaking ocean waves, particles of smoke from fires both natural and human-made. These particles are so small and so light that they remain suspended in the air almost indefinitely, invisible to the eye, carried on currents of wind across enormous distances. When rising water vapor encounters these particles and the temperature is right, it clings to them. The vapor condenses around the particle, surrounding it, coating it in a thin film of liquid water, and in doing so, transforms from invisible gas into something real and visible. A droplet is born. Each one of these cloud droplets is extraordinarily small. Far too small to fall as rain. Far too light to do anything but drift. But there are not just a few of them. A single cloud contains millions upon millions of individual droplets, each one gathered around its tiny core particle, each one suspended in the churning air. And together, in their millions, they become visible. They become what we look up at. A cloud. The formation of a cloud is not a sudden event. It is a gradual accumulation, a slow gathering of almost weightless things until their combined presence becomes impossible to ignore. Within that gathering, the physics becomes surprisingly intricate. The droplets are not simply floating in still air. Clouds are dynamic, turbulent environments, full of tiny swirling motions, miniature vortices, small eddies of moving air that bring particles and droplets into closer contact with one another. These vortices are not random chaos. They play a genuine role in how clouds develop. By drawing water-coated particles together, they encourage collisions, encourage clustering, encourage the slow process by which small droplets begin to combine into larger ones. In warm clouds, those that exist entirely below the freezing level, where no ice is involved, the dominant process shaping rainfall is called collision and coalescence. Larger droplets fall slightly faster than smaller ones. As they descend through the cloud, they collide with smaller droplets in their path and absorb them, growing heavier with each collision, falling faster, collecting more. It is a process of accumulation, slow at first, then accelerating, a kind of gathering momentum that mirrors the way many things in nature grow. Not every part of a cloud participates equally in this. Within a cloud's interior, particularly near its core, the droplets tend to be larger. The conditions there, the density of moisture, the patterns of air movement, favor growth. The core of a cloud is where the most significant development happens, where drops are working their way toward a size that might, eventually, allow them to fall. The distribution of drop sizes within a cloud is not just a detail. It determines the character of what comes next. Clouds where droplets are relatively uniform in size tend to produce light, steady precipitation, the kind of gentle rain that falls for hours, soaking slowly into the ground. Clouds where there is a wide range of drop sizes, where large and small coexist and collide in greater numbers, can produce heavier, more intense rainfall. The internal architecture of a cloud, the sizes and arrangements of its countless droplets, contains, encoded within it, the nature of the storm it may become. There is something deeply calming about understanding rain this way, not as something that simply happens, but as something that builds. Slowly. Quietly. Particle by particle, droplet by droplet, collision by collision. Long before a single drop of rain reaches the ground, an enormous and delicate process has been unfolding high above, in the cold and cloud-filled air. The sky is not empty. It is full of water in motion, water in transition, water gathering itself toward the moment of falling. And that moment is getting closer. For most of human history, everything we understood about clouds came from observation at a distance. We watched them build on the horizon, felt what fell from them, measured rain in gauges on the ground. What happened inside a cloud, the invisible architecture of droplets and ice crystals, the churning internal dynamics, remained largely a matter of inference and theory. That has changed profoundly in recent decades. Satellites now carry instruments capable of looking down through the atmosphere with extraordinary precision, building detailed three-dimensional pictures of precipitation as it forms and falls. Scientists can observe the internal structure of a cloud system from space, mapping where large drops are forming, where ice crystals are growing, how a storm is organizing itself from the inside out. Individual raindrops and snowflakes, in their billions, are no longer invisible to us. They are data. They are mappable. The sky has become, in a sense, transparent to those who know how to look. And what that closer looking has revealed, above almost everything else, is the importance of something that was long underestimated. Updrafts. Rising columns of air moving upward through a cloud were understood, of course, they had always been part of the picture. But the degree to which updrafts shape rainfall, the degree to which they determine what kind of rain falls, how heavy it is, how long it lasts, has become much clearer as our tools for measuring them have improved. An updraft is exactly what it sounds like, air moving upward. But within a cloud, that upward motion is not uniform. It varies, in strength, in width, in duration, and those variations have profound consequences for the drops forming within it. Over land, where surface heating is more intense and the atmosphere tends to be more unstable, updrafts are often strong. They push upward with enough force to hold developing raindrops aloft for longer, giving them more time to grow through collision and coalescence before their weight finally overcomes the rising air. This is why land-based storms often produce heavier, larger raindrops. The updrafts act as a kind of slow elevator, holding drops in the optimal growing zone, suspended in a region of dense moisture, until they have grown large enough to fall with real weight. Over the ocean, the picture is different. Updrafts there tend to be gentler, weaker, more diffuse. Without the strong lifting force of intense surface heating, developing drops are not held aloft as long. They begin to fall sooner, at a smaller size, producing drizzle, that fine, soft, almost misting rain familiar to anyone who has spent time near the sea. Ocean drizzle and continental downpours are, in a sense, the same process operating under different conditions. The difference lies largely in the strength of the air that supports the forming drops. Drop size, then, is not simply a product of how much moisture is present. It is intimately connected to the speed of the air moving upward through the cloud. A faster updraft means more time aloft, more collisions, more coalescence, a larger final drop. A slower updraft means an earlier descent, less growth, a finer, lighter rain. The vertical speed of invisible air determines the weight of what eventually falls on the ground. Turbulence adds another layer to this. Within a cloud, air does not simply rise smoothly in a steady column. It churns and eddies, rolls and spirals. And this turbulence, which might seem like mere disorder, actually plays a constructive role. It brings drops into contact with one another more frequently than smooth laminar flow would allow. It increases the rate of collision. In the complex, restless interior of a developing storm, turbulence is not an obstacle to raindrop growth, it is one of its engines. In the most powerful storms, this process reaches a remarkable scale. Thunderstorm updrafts can reach speeds that are difficult to intuitively grasp, strong enough, in extreme cases, to support hailstones the size of golf balls, holding them suspended against gravity while they accumulate layer after layer of ice. The largest raindrops form in these same powerful updrafts. Drops that have had time, and support, and turbulent energy behind them, drops that have grown through hundreds or thousands of collisions before finally becoming too heavy for even the storm's considerable lifting power to sustain. When you see very large individual raindrops falling during a storm, the kind that hit a surface with a distinct, almost audible impact, you are seeing evidence of what was happening high above. Large drops are a signature of strong updrafts. They are also a signal of something else, significant turbulence and the likelihood of gusty, shifting winds near the storm. Pilots know this. Meteorologists know this. The size of a raindrop, read correctly, is a message from the interior of the storm that produced it. There is a curious extreme at the upper end of updraft strength. In the most powerful thunderstorms, the updraft can be so intense that drops forming within it cannot fall at all. They are carried upward faster than gravity pulls them down, swept into the higher reaches of the storm system, sometimes ejected out through the anvil-shaped tops of cumulonimbus clouds at extraordinary altitudes. The storm, in a sense, holds its own rain prisoner, at least temporarily, in the grip of rising air. It takes a particular kind of vastness to produce what a fully developed thunderstorm produces. A single large thunderstorm, over the course of its lifetime, releases trillions of individual raindrops. The number sits so far beyond everyday experience that it barely registers as a number at all. Trillions of droplets, each one having formed around a tiny particle of dust or pollen or sea salt, each one having grown through collisions in the cold and turbulent interior of the cloud, each one eventually reaching a size and weight that the updraft could no longer support. And then, one by one and in their countless billions, they begin to fall. Each drop a small, separate thing. Each one carrying within it a tiny history of its own formation, the particle it gathered around, the collisions it survived, the updrafts that held it and finally released it. Falling now, through thousands of meters of open air, toward whatever surface waits below. The storm is not one event. It is trillions of tiny ones, happening simultaneously, each following the same quiet physics, each part of the same vast and ancient cycle that has been running, since long before there was anyone to watch it fall. There is a moment inside every cloud, unhurried, invisible, occurring in the cold air far above any ground, when something tips from potential into reality. What a collection of microscopic particles and clinging vapor crosses a threshold and becomes something recognizable. Something falling. Something real. That moment is the birth of a raindrop. And like most births, it is not a single instant but a long accumulation of smaller events. Growth through collision is the essential story of how a raindrop comes to exist. It begins almost incomprehensibly small. A dust particle, a fragment of soil lifted from a dry field, a grain of sea salt, a speck of pollen carried on the wind, enters a region of the cloud where water vapor is ready to condense. The vapor gathers around it, clings to it, builds up on its surface in a film so thin it is barely measurable. What exists now is a cloud droplet. It is perhaps a few micrometers across. To give that scale some meaning, a human hair is roughly 70 micrometers wide. This droplet is smaller than the width of that hair by a factor of 10 or more. It is not yet a raindrop. It is barely anything at all. But the cloud around it is full of other droplets just like it, millions of them per cubic meter of air, all drifting, all suspended, all subject to the same gentle forces. And the cloud is not still. Air moves within it in complex currents, rising here, descending there, swirling in small eddies driven by temperature differences and the release of heat as water vapor condenses. These air movements bring droplets into contact with one another. When two droplets collide and merge, the resulting droplet is slightly larger than either of its predecessors. Larger droplets fall marginally faster through the air, which means they encounter more droplets in their path, which means they grow faster, which means they fall faster still. This is the self-reinforcing cycle at the heart of raindrop formation. Slow at first, then gathering momentum, a tiny droplet works its way upward through orders of magnitude. From micrometers to fractions of a millimeter. From fractions of a millimeter to a millimeter. Growing not through any single dramatic event but through an accumulation of small encounters, each one adding a little more water, a little more weight. By the time a drop has grown to about a millimeter in diameter, the lower end of what we would recognize as an actual raindrop, it has absorbed approximately 1 million of the tiny cloud droplets that were its starting material. 1 million. That figure is worth dwelling on. Every raindrop that has ever dampened your skin or darkened a pavement or struck the surface of a still pond was, not long before, 1 million separate microscopic things. The drop that falls is the product of an immense, invisible act of gathering. As a growing drop descends through lower levels of a cloud, it often passes through regions of mist and lighter precipitation, zones where smaller droplets are still suspended, still drifting, still available to be absorbed. Falling through this mist allows further growth even after the drop has begun its descent. The journey downward is not always a straight passage through empty air. It can be an additional growing period, a last accumulation of mass and weight before the drop emerges from the base of the cloud and enters the open sky. There comes a point at which the drop is simply too heavy for the cloud to hold. The updrafts that once supported it are no longer sufficient. The balance between rising air and gravitational pull tips decisively, irreversibly, in favor of gravity. And the drop falls. This is precipitation, water returning to the surface of the earth after its long suspension in the atmosphere. In its simplest form, it is gravity asserting itself over a droplet that has grown beyond what the air can support. But the form that precipitation takes when it arrives at the ground depends entirely on the conditions it encounters during its descent. In warm air, all the way from cloud base to surface, the drop falls as liquid rain. Nothing interrupts its liquid state. It arrives as water, as it was when it left the cloud. But if the air below the cloud is cold enough, the falling drop may freeze before it reaches the ground, arriving as sleet or ice pellets. If it freezes and is caught in an updraft and carried back upward into the cloud, it may accumulate layers of ice and descend again, only to be lifted once more, repeating this cycle until it has built up enough mass to fall with enough speed that the updraft cannot reclaim it. This is how hail forms, through repeated cycling, through repeated accretion of ice, each layer recording another pass through the storm's interior like rings in a cross-section of wood. And in cold conditions, when the air is below freezing from cloud to ground, the water vapor may bypass the liquid state entirely, depositing directly onto ice crystals in an intricate, branching geometry. Snowflakes. Each one a different expression of the same underlying physics, shaped by the precise temperature and humidity conditions encountered at each stage of their formation. No two exactly alike, not because of any mystical quality, but because no two crystals travel through precisely the same sequence of conditions on their way down. Rain, snow, hail. Three versions of the same essential journey: water that rose from the surface, gathered in the sky, and found its way back down. The form is a detail, in one sense. The return is the constant. Now, there is something that almost everyone believes about raindrops that turns out to be beautifully, simply wrong. The image is familiar. A teardrop, rounded at the bottom, tapering to a point at the top. It appears on umbrella patterns and weather icons, in children's drawings, in the universal visual shorthand for rain. It feels correct. It looks correct. And it is, according to the actual physics of falling water, not correct at all. Raindrops are not tear-shaped. The shape of a falling raindrop is determined by two competing forces. On one side, surface tension, the tendency of water to pull itself inward, to minimize its own surface area, to form the most compact shape available. Left entirely to surface tension with no other forces acting on it, a drop of water becomes a perfect sphere. This is why water beads on a smooth surface. This is why droplets hanging from the tip of a leaf are round. Surface tension is a powerful and elegant force, and its preference is always for the sphere. But a falling raindrop is not floating in stillness. It is moving through air, and that air resists it. As the drop falls, air pressure builds against its lower surface, the face of the drop that is leading its descent. This pressure pushes upward against the bottom of the drop, flattening it. Meanwhile, the top of the drop, sheltered from the direct impact of the oncoming air, retains more of its curvature. The result is a shape that has no perfect name in everyday language. It is somewhat like the bottom half of a sphere flattened into a more horizontal plane, while the top retains a fuller, more rounded dome. Imagine a very small hamburger bun, or a sphere that has been gently pressed from below. This is what a raindrop looks like in free fall. Not a teardrop. Not a perfect sphere. Something in between, a shape defined by the balance of forces acting on it from moment to moment. And that balance shifts depending on size. Small drops, those at the lower end of raindrop dimensions, are almost perfect spheres. They are light enough that the air pressure acting on them during their fall is minimal compared to the pull of surface tension. Surface tension wins, and the sphere is maintained. As drops grow larger, the contest becomes more even. A drop of 2 or 3 millimeters begins to show clear flattening on its underside. Its shape becomes noticeably oblate, wider than it is tall, with a distinctly flattened bottom profile. The sphere has been compromised by the resistance of the air, and the resulting form is something more nuanced, more responsive to its environment. And at the largest scales, drops approaching 5 or 6 millimeters, which represent the upper limit of raindrop size before other forces intervene, the shape becomes quite dramatic. The base of the drop flattens severely. The sides bulge outward. In some cases, the very center of the bottom surface can develop an upward dimple, pushed inward by air pressure as the drop's descent speed increases. These largest drops no longer resemble any simple geometric form. They are active, dynamic structures, constantly adjusting their shape in response to the air rushing past them. They wobble. They oscillate. They are, in a physical sense, in conversation with the atmosphere through which they fall. There is something quietly wonderful about this. The shape of a raindrop, something so small, so fleeting, something most of us have never actually observed in detail, is the result of a genuine physical negotiation. Surface tension pulling inward. Air pressure pushing upward and outward. Gravity pulling the whole thing down. These three forces, acting simultaneously on a volume of water measured in cubic millimeters, produce a shape that is neither what intuition predicts nor what simplicity would suggest, but something more interesting than either. Every raindrop falling through open air is a small, temporary resolution of competing forces. A shape that exists only because it is falling, only because air is resisting it, only because water has the particular surface properties that it does. If any of those conditions changed, if gravity were weaker, if the atmosphere were denser, if water's molecular bonds were slightly different, the shape would be different too. What falls on your roof? What darkens the window beside you? What fills the puddles on a quiet street after an evening storm? Each drop is a tiny, impermanent sculpture. Shaped by physics. Formed in cold air far above. Carrying within its form the evidence of everything that acted upon it during its long journey down through the sky. And it is still falling. Still changing shape as it descends. Still negotiating, in its wordless way, with the air around it. Still becoming what it will be when it finally arrives. As a raindrop grows, its shape tells a story of increasing tension, a quiet structural drama playing out over a few seconds of freefall, invisible to anyone watching from below. A drop of around 3 millimeters across has moved well past the near-perfect sphere of its smaller counterparts. It has taken on something closer to the shape of a jelly bean, rounded on top, noticeably flattened beneath, slightly elongated along its horizontal axis. It is a shape that still has coherence, still holds together with a kind of compact integrity. Surface tension is still managing the situation. The drop is distorted, but it is stable. It falls with a kind of quiet confidence, its form continuously adjusted by the forces acting on it but never fundamentally threatened by them. But drops do not stop growing at 3 millimeters. In the right conditions, strong updrafts, dense cloud moisture, the turbulent interior of a heavy storm, they continue to absorb smaller droplets, to accumulate, to grow heavier and wider. And as they do, the balance of forces that kept the jelly bean shape manageable begins to shift in a more consequential direction. A drop approaching 4 or 5 millimeters in diameter enters genuinely unusual physical territory. The flattening of the base becomes extreme. The sides push outward. The overall form begins to resemble something far less tidy than a jelly bean, something more open, more spread, more architecturally precarious. Observers who have studied high-speed photography of large falling drops have reached for two images to describe what they see at this scale: an umbrella or a jellyfish. Both comparisons capture something real. Like an umbrella, the large drop develops a dome shape on top with edges that curve outward and slightly downward. Like a jellyfish, it has a kind of billowing, trailing quality, wide and rounded above, with the suggestion of something being pushed from below. It is a shape under considerable stress. You can see, even in a still image, that this is a form at the edge of its own coherence. The air pressure acting on the base of the drop at this size is no longer simply flattening it. It is doing something more structurally significant. It is beginning to push the center of that flattened base upward, into the body of the drop itself. A depression forms, a dimple, then a deeper indentation, then something approaching a hollow. The drop is developing a concave underside while its rim continues to bulge outward. What was a solid, compact volume of water is reorganizing itself into something thinner, more spread, more membrane-like at its edges. Surface tension, which has been managing the shape of this drop since its earliest moments in the cloud, is now fighting a losing battle. It still pulls inward. It still tries to minimize surface area, to restore compactness, to hold the water together in the most efficient shape available. But the forces working against it, the air pressure from below, the inertia of the drop's own mass, the dynamic pressure of its descent, have grown too large to be overcome. Surface tension is not failing suddenly or catastrophically. It is simply being outpaced. The membrane at the drop's base grows thinner as the central depression deepens and the rim expands outward. What was a robust volume of water has become, in its largest regions, a thin sheet, a nearly transparent skin of water stretched across a widening area, held together by surface tension that is increasingly insufficient to the task. This thinning membrane is fragile in a way that the original compact drop was not. Small disturbances, a slight turbulence in the air, a minor asymmetry in the drop's internal water distribution, are enough to trigger what comes next. The thin sheet of water at the base of the drop ruptures. The carefully maintained structure that has been building since that first condensation around a dust particle loses its integrity in a fraction of a second. The large drop breaks apart. This breakup is not violent, exactly, but it is definitive. The single large drop fragments into a collection of smaller drops, some medium-sized, some small, a brief mist of the very finest droplets. Each fragment inherits its own surface tension, its own momentum, its own trajectory. Each becomes, immediately, its own falling entity, subject to the same forces that govern its parent. Some of these fragments will grow again through further collisions. Others will evaporate before reaching the ground. The population of raindrop sizes in any given storm reflects, in part, the accumulated history of countless such breakup events, large drops forming, growing unstable, fragmenting, with their fragments either falling to ground or beginning the growth process again. This is one of the reasons why rain contains drops of so many different sizes simultaneously. It is not simply that different drops started growing at different times or in different parts of the cloud, though that is also true. It is that the largest drops are constantly breaking apart and reseeding the population with medium and small drops, which may in turn grow and break again. Raindrop size distribution in a storm is a dynamic, constantly refreshing balance between growth and fragmentation. The long-held understanding among scientists was that 4 mm represented roughly the practical upper limit for a stable raindrop in natural conditions. Below that threshold, the forces maintaining the drop's integrity were generally sufficient. Above it, breakup became increasingly inevitable. 4 mm was presented as a kind of ceiling, not a hard rule, but a useful boundary, grounded in an understanding of when surface tension reliably loses its contest with air pressure and drop inertia. This figure came directly from observed breakup dynamics. It was not arbitrary. It reflected something real about the physics of water falling through air at terminal velocity. And for a long time, it was treated as settled. Then measurements came in that challenged the ceiling. In Brazil, above the Amazon rainforest, and in Hawaii, researchers using specialized instruments to measure falling precipitation detected drops of extraordinary size. Not 4 mm. Not 5, or 6, or even 7. The largest individual drops measured in these studies reached 8.8 mm in diameter, more than twice the old rule of thumb limit, and larger than anything standard models had predicted could survive the descent from cloud to ground without breaking apart. 8.8 mm. To hold that scale in mind, the diameter of a standard pencil eraser is roughly 5 or 6 mm. These drops were larger than that. They were, by any measure, enormous for falling water. And they were real, not a measurement error, not an anomaly of instrumentation, but actual drops of liquid water that had somehow maintained their coherence through conditions that should, by prior understanding, have torn them apart long before they reached the measuring equipment. How did they survive? The leading explanations point to unusual circumstances, extremely short fall distances between cloud base and measurement point in some locations, meaning the drops had less time to become unstable, and in the Amazon specifically, the presence of large condensation nuclei associated with smoke particles from fires, which may have altered the drop's internal structure in ways that gave it slightly more resistance to breakup than ordinary drops. Whatever the mechanism, the discovery matters because it reminds us that nature operates at the edges of our models as well as within them. The physics of raindrop breakup is well understood in its broad outlines. But the extreme cases, the places where conditions are unusual, where measurements yield numbers that don't fit neatly into existing frameworks, reveal that there is always more detail, always more complexity, always another layer beneath the layer we thought was the bottom. A raindrop is a small thing. It weighs a fraction of a gram. It exists for seconds. And yet within its brief, falling life, it enacts a surprisingly rich sequence of physical processes: formation, growth, distortion, potential breakup, each governed by forces that have been studied for over a century and are still, at their outer limits, capable of producing surprises. The next time you watch rain fall on glass, the way a large drop spreads and flattens on contact, the way smaller drops remain more rounded, the way some seem to race downward while others hesitate, you are watching the aftermath of all of this. Every drop that reaches the surface carries the history of its own formation written in its size, its shape, its speed. A physical record of everything that happened in the cold air above. Still falling. Still arriving. Each one a small completion of a journey that began with a particle too small to see and ends with a sound soft enough to sleep to. The discovery of 8.8 millimeter drops in nature raised an obvious question among researchers. If drops that large could form and fall under the right atmospheric conditions, what was the actual upper limit? Was there one? And could it be explored in a more controlled setting? The answer came from the laboratory. Scientists working with specialized equipment, carefully controlled chambers, high-speed cameras, precision instruments for measuring drop dimensions, managed to produce and observe drops of 10 millimeters in diameter. A full centimeter of water, held together by surface tension against gravity and the resistance of air. Drops of this size do not occur in nature under ordinary conditions. The atmosphere rarely provides exactly the right combination of circumstances to allow something so large to form and travel any meaningful distance without breaking apart. But in the contained, adjustable environment of a laboratory, where fall distances could be minimized and conditions carefully managed, 10 millimeter drops became possible. What these experiments confirmed was not simply that large drops could be made. They also shed light on how such drops form in the first place, and what they actually represent in physical terms. The key, it turns out, is the condensation nucleus, the particle around which the drop first forms. Ordinary cloud droplets condense around tiny particles, fragments of mineral dust, sea salt, pollen, the finest products of combustion. These particles are typically measured in fractions of a micrometer. They are, for practical purposes, as small as particles can be while still being detectable. But not all particles suspended in the atmosphere are that small. Smoke from large fires, particularly the intense, sustained burning of forests or grasslands, can waft particles into the atmosphere that are significantly larger than the typical condensation nucleus. These larger particles provide a larger initial surface for condensation, allowing drops to begin their growth from a more substantial starting point. Instead of building upward from almost nothing, a drop forming around a large smoke particle begins with a meaningful foundation. It reaches significant sizes faster, and may be able to maintain its integrity at sizes that would be impossible for a drop that started smaller. This is the leading explanation for the extraordinary drops measured over the Amazon, a landscape where large-scale burning has been common, where the atmosphere above the forest is periodically loaded with smoke particles of unusual size. Those particles became the seeds of drops that broke the expected rules. The fire, in a grim and unintended way, contributed to the formation of record-breaking raindrops. There is something worth noting about the actual volume of water in these giant drops. A 10 millimeter drop sounds dramatically larger than a 4.5 millimeter drop, more than twice the diameter. But the relationship between diameter and volume in a sphere is not linear. Volume scales with the cube of the radius. This means a drop with twice the diameter contains not twice the water, but 8 times the water. A single 10 mm drop contains roughly the same volume of water as an entire 4.5 mm sphere to the third power, a striking reminder that the largest natural drops are not just slightly bigger than average. They are, in terms of the water they carry, enormously larger. A handful of such drops delivers as much water as hundreds of smaller ones. It is one of those mathematical truths that seems surprising until the geometry is clear, and then seems inevitable. But laboratory curiosities and record-breaking extremes aside, the vast majority of raindrops that have ever fallen on Earth have been far smaller and far more ordinary. And their journey through the open sky, from the base of a cloud to the surface below, follows a physical logic that is elegant in its simplicity and surprisingly rich in its detail. When a drop first forms and begins to fall, gravity takes hold of it immediately and without negotiation. The drop accelerates. This is the straightforward part, the same force that governs every falling object, from a stone dropped from a bridge to a leaf drifting from a tree. Gravity pulls the drop downward, and in the first moments of its descent, its speed increases steadily. But air is not nothing. Air has density. Air has viscosity. As the drop moves faster, the air it passes through pushes back against it with increasing force. This drag, the resistance of the atmosphere to the drop's passage, grows as speed grows. And at some point, for every drop of every size, a balance is reached. The downward pull of gravity and the upward push of air resistance become equal. The drop stops accelerating. Its speed becomes constant. This constant speed is called terminal velocity. And for raindrops, it is one of the most practically significant numbers in the physics of precipitation. For a typical raindrop, one in the size range most commonly associated with moderate rainfall, terminal velocity falls somewhere between 15 and 25 miles per hour. In metric terms, a commonly cited figure for an average-sized drop is around 9 meters per second. Translated back into more intuitive units, this is roughly 20 miles per hour, or about 14 miles per hour when averaged across the full range of drop sizes found in typical rain. These are not especially fast speeds. A gentle jog is about that fast. A cyclist moving at moderate pace through a park is moving at roughly the same speed as a falling raindrop. And yet rain feels purposeful, feels like it arrives with intention, because it falls from such heights, from cloud bases that may be hundreds or thousands of meters above the surface, and because it arrives in such quantity that even moderate speed, multiplied across trillions of drops, carries considerable energy. The relationship between drop size and terminal velocity is direct and consistent. Larger drops fall faster. Smaller drops fall slower. This is not surprising, it follows logically from the balance between gravitational force and air resistance. But the range across the spectrum of natural drop sizes is quite striking. A larger drop, measuring several millimeters in diameter, falls at several meters per second. It arrives at the surface with meaningful force, making an audible impact, splashing visibly, doing real physical work on whatever surface it strikes. A smaller drop, one at the finer end of what still qualifies as rain rather than mist, may fall at under 1 meter per second. Less than a slow walk. These drops drift more than they fall. They arrive softly, almost apologetically, making no sound worth noticing, leaving only the finest dampness on a surface. Drizzle occupies a distinct category. Drizzle drops are small, typically less than half a millimeter in diameter, sometimes far smaller, and they fall at around 2 meters per second. This slow, gentle descent is part of what makes drizzle feel different from rain. It does not arrive decisively. It accumulates gradually, almost invisibly, coating surfaces in a fine, even moisture that seems to appear without any obvious source. You step outside and find yourself damp without ever feeling a drop land. That is drizzle doing what it does, falling slowly enough that individual impacts are imperceptible, present everywhere and nowhere in particular. The range from drizzles 2 meters per second to a large raindrops 9 or 10 meters per second might seem modest in absolute terms. But in terms of the physical impact on surfaces, on soil, on water bodies, on plants and pavements and skin, the difference is enormous. The energy of impact scales with the square of velocity, meaning a drop falling at 9 meters per second carries not 4.5 times the impact energy of a drop falling at 2 meters per second, but more than 20 times as much. Large, fast drops do real mechanical work. They dislodge soil particles. They break the surface tension of puddles. They make the sound we call rain, that particular soft percussion on rooftops and leaves and window glass that, for so many people, is one of the most naturally soothing sounds in the world. Small, slow drops do none of that. They settle rather than strike. They coat rather than splash. Their relationship with surfaces is gentle almost to the point of tenderness. Both are the same water. Both have made the same journey from ocean to cloud to open sky. The difference between them, the difference between a cold, driving rain and a barely perceptible drizzle, comes down, in the end, to size. To how long a particular drop spent in a cloud, how many collisions it survived, how strong the updraft was that held it aloft. The whole character of a rainstorm, the whole experience of standing beneath it, is shaped by processes that were completed before a single drop left the cloud. By the time rain reaches you, by the time you feel it on your face or hear it on the roof or watch it run in rivulets down a window, its essential nature has already been decided. You are experiencing the outcome of decisions made in cold air far above, in the dark interior of a cloud you may never have seen. The rain that reaches you is already, in a sense, finished. Already itself. Already exactly what it is going to be. Falling through the last few hundred meters of open sky now. Getting closer. The ground waiting below, patient and still, as it always has been. The spectrum of falling speeds across the range of natural raindrop sizes is narrower than intuition might suggest, but within that range, the differences are consistent and measurable, and they tell us something precise about the physics governing each drop's descent. A small raindrop, one sitting at around 1.5 millimeters in diameter, which places it near the smaller end of what counts as rain rather than drizzle, reaches a terminal velocity of approximately 7 meters per second. This is a drop that is light enough to be meaningfully slowed by air resistance, but substantial enough to fall with some purpose. 7 meters per second is roughly 25 kilometers per hour. fast enough to feel on skin, fast enough to make a faint sound on a leaf, but not, in the context of falling objects, particularly dramatic. A large raindrop, one at around 6 millimeters in diameter, approaching the upper range of what can survive intact through a meaningful fall, reaches terminal velocity of close to 10 meters per second, 36 kilometers per hour. That is a noticeable increase. The difference between 7 and 10 meters per second might seem small as numbers, but in terms of impact energy, which scales with the square of velocity, that larger drop carries more than twice the kinetic energy of the smaller one. The surface it strikes feels the difference. 6 millimeter drops averaging around 10 meters per second represents a kind of practical ceiling for natural rainfall. Drops larger than this are rare, unstable, and short-lived in their large form. Most of the rain that falls on the world falls in the range between these two figures, between the gentle 7 meters per second of small drops and the more purposeful 10 meters per second of large ones. The variability is real, but it is bounded. What determines exactly where within this range a given drop settles is not just size. The atmosphere through which the drop falls is not a fixed medium. It varies in temperature, in pressure, in density, all of which affect how much resistance the air offers to a falling object. Temperature matters because warmer air is less dense than cooler air. A drop falling through warm, low-density air encounters less resistance per unit of its cross-sectional area, which means drag builds more slowly and terminal velocity is slightly higher. The same drop falling through cold, dense air meets more resistance and settles at a slightly lower speed. The difference is not enormous, but it is real and measurable, particularly when comparing drops falling through a cold winter atmosphere versus the warm, humid air of a tropical storm. Pressure matters for similar reasons. At higher altitudes, where atmospheric pressure is lower and air is thinner, drag is reduced and drops fall faster than they would at sea level. A raindrop falling from a cloud over a high-altitude plateau moves through air that offers less resistance than the air at a coastal location, and its terminal velocity reflects this. The physics is the same. The medium it operates in is different. At the heart of all of this is a quantity called the drag coefficient, a dimensionless number that captures how aerodynamically efficient or inefficient a given shape is as it moves through a fluid. For a raindrop in the size range relevant to most rainfall, the drag coefficient sits at roughly 0.5. This number reflects the drop's somewhat flattened, oblate form, not as streamlined as a teardrop, more resistant to airflow than a perfect sphere would be. It is a number that encodes, in a single figure, the complex interaction between the drop's shape and the air it pushes through. The terminal velocity of any falling object is reached when the drag force, which depends on the drag coefficient, the density of the air, and the square of the falling speed, exactly equals the gravitational force pulling the object downward. At that balance point, there is no net force, no acceleration. The object falls at constant speed. For a raindrop, this equilibrium is reached relatively quickly after the drop leaves the cloud base, and from that point on, the speed simply holds. It holds, that is, unless something disturbs it. And the atmosphere is rarely entirely calm. There is an interesting comparison worth making here. simply because it puts the scale of raindrop terminal velocities in perspective. A human body in freefall, the kind of freefall experienced during a parachute jump before the parachute opens, reaches a terminal velocity of roughly 50 to 55 meters per second in a standard belly-to-earth position. More than 200 kilometers per hour. 5 or 6 times faster than the fastest raindrop. The human body, with its mass of 60 or 70 or 80 kilograms, falls through air with an enormous gravitational force relative to its drag. A raindrop, with its fraction of a gram mass and its proportionally large surface area, is slowed by drag to a degree that a falling human simply is not. This comparison makes intuitive sense when you think about it from the perspective of scale. Small, light objects are dominated by drag. Large, heavy objects are dominated by gravity. A raindrop sits firmly in the category where air resistance is the dominant factor shaping its motion. A falling person does not. The physics are the same, the proportions are radically different. Now, one detail about the descent of real raindrops that is easy to overlook: they do not fall in clean, stable, perfectly oriented positions. They tumble. As a drop falls through air, it is subject to small instabilities, asymmetries in the airflow around it, minor variations in its own shape, the slight turbulence of the atmosphere it passes through. These instabilities cause the drop to oscillate, to wobble, to rotate as it descends. It does not spin in a clean, controlled way. It tumbles in a somewhat irregular fashion, constantly shifting its orientation relative to the direction of fall. This tumbling has a consequence that might not be immediately obvious: it increases the drop's average drag. A tumbling drop presents different cross-sectional profiles to the oncoming air at different moments in its rotation. Sometimes it presents its widest face, its flattened underside, directly to the airflow, which maximizes drag. Sometimes it presents a narrower profile, reducing drag momentarily. The net effect of this irregular tumbling, averaged over the course of the fall, is a drag that is somewhat higher than a perfectly stable, non-rotating drop of the same size would experience. This means that real raindrops fall slightly more slowly than theoretical calculations for a smooth, stable sphere of the same mass would predict. The tumbling introduces additional resistance. It is one of several reasons why precise modeling of raindrop terminal velocities requires empirical measurement rather than pure calculation. The real behavior of real drops is messier than any idealized model, and the messiness matters. What all of this describes is a drop falling vertically, or as close to vertically as physics and atmospheric conditions allow. But in practice, raindrops almost never fall in perfectly vertical straight lines. The atmosphere through which they descend is rarely still. Wind is almost always present at some level, sometimes gentle and consistent in direction, sometimes gusty and variable, sometimes organized into large-scale flows that can carry precipitation sideways for significant distances. Horizontal wind alters the path of a falling raindrop in a direct and simple way. The drop's motion through the air has two components: a downward component driven by gravity and resisted by drag, and a horizontal component driven by whatever wind is present at the drop's altitude. These two components combine into a single diagonal trajectory. The stronger the wind, the more diagonal the path. In a strong horizontal wind, a raindrop that originated directly above a point on the ground may actually reach the surface several meters or more to one side of where it started its descent. This is why rain in windy conditions feels and behaves so differently from rain in still air. The drops are arriving not from directly above but from an angle, driven horizontally by wind even as gravity pulls them down. They strike surfaces, faces, leaves, windows, pavements, at an angle rather than vertically. They penetrate under eaves and overhangs that would otherwise provide shelter. They arrive from a direction as much as from a height. In very strong winds, the horizontal component of a raindrop's velocity can actually exceed its vertical component. The rain moves more sideways than down. This is the rain of serious storms, of gales and squalls, rain that seems to come at you rather than fall on you. The drop is still obeying the same physics it always has: gravity downward, drag-resisting motion, wind adding a horizontal push. But the balance between those forces has shifted to a point where the rain's behavior becomes something qualitatively different from the gentle vertical fall of a calm evening shower. For all the complexity, the varying speeds, the tumbling, the wind-altered paths, the temperature and pressure adjustments, there is something grounding in the underlying simplicity of what is happening. Gravity pulls. Air resists. Wind pushes. The drop falls in the direction that the sum of these forces dictates, at the speed where drag and gravity are equal, tumbling slightly as it goes. Each drop is solving, in real time, a continuous equation whose variables include its own size and shape, the density and movement of the air around it, and the invisible pull of a planet far larger than itself. The answer to that equation is the raindrop's path. And every path ends at the surface, arriving softly or forcefully, vertically or at a steep angle, on soil or stone or water or leaf, at the precise moment and place where all the forces acting on it have brought it to rest. Just ahead now. Just a little further to fall. Wind does not simply push a raindrop sideways. It changes the drop itself. This is one of the less obvious consequences of wind on precipitation, and it follows from the physics of how drops grow. In still air, a falling drop descends through whatever population of smaller droplets and moisture happens to be directly in its path below it. The zone of possible collision is limited by the drop's size and its straight downward trajectory. But when horizontal wind is added to the picture, the drop is no longer moving only downward. It is moving through the air at an angle, sweeping through a larger volume of the atmosphere per unit of time than it would in calm conditions. This increased sweep rate means more collisions with smaller droplets. More collisions mean more coalescence. More coalescence means a larger drop. Wind, by altering the path of a falling raindrop, gives it more opportunities to grow. The result is measurable. In windy conditions, raindrops tend to be larger in diameter than in calm conditions, even when the cloud producing them is otherwise identical. The atmosphere's horizontal motion is, in effect, accelerating the drop's growth. And a larger drop falls faster. So the same wind that makes the drop bigger also, indirectly, through the growth it enables, makes the drop heavier and therefore faster. Diameter and terminal velocity both increase together, driven upward by the same cause. The wind strengthens the rain in two ways simultaneously, and the two effects reinforce each other. The angle at which rain falls is the most visually obvious consequence of wind, and it changes continuously as wind conditions change. In light, variable winds, rain falls at a gentle diagonal, mostly downward, slightly angled. In moderate steady winds, the diagonal becomes more pronounced. In strong winds, rain can arrive nearly horizontally. The falling angle is simply the geometric result of combining the vertical velocity, set by terminal velocity, which depends on drop size, with the horizontal velocity imparted by the wind. Change either component and the angle changes. What this means practically is that the surface a raindrop strikes in windy conditions is not the same as the surface it would strike in calm air, even if the raindrop originates in exactly the same place. A drop that begins its fall directly above an open field may, in strong crosswinds, travel hundreds of meters horizontally before reaching the ground. The raindrop's final destination is determined not just by where it formed but by everything the wind did to it along the way. The kinetic energy of a raindrop, the energy it carries by virtue of its motion, rises dramatically with wind speed, and this is where the physical consequences of wind on rainfall become most significant. Kinetic energy depends on both mass and velocity. Since wind increases both the size of drops and their total speed of travel through the air, its effect on kinetic energy is compounded. A drop that is larger has more mass. A drop moving faster through a combination of terminal velocity and horizontal wind has more total velocity. Both factors feed into kinetic energy simultaneously. The result is that wind-driven rain carries substantially more energy per drop than calm rain does, even when both are produced by similar clouds. This energy difference has real consequences for the surfaces rain strikes. Soil exposed to wind-driven rain erodes more rapidly. The mechanical impact of large, fast, wind-driven drops dislodges soil particles with far greater force than gentle vertical rain. On plants, on structures, on the surface of standing water, the difference between calm rain and wind-driven rain is not simply one of direction or inconvenience. It is a difference in physical force, in how much work the rain is doing on the world it strikes. But before any of that impact, before the drop reaches any surface at all, there is simply the fall itself. The long, quiet descent through open air that follows the drop's departure from the cloud base. How long does that fall actually take? The answer, it turns out, varies considerably, and some of the timescales are longer than most people would guess. For a typical raindrop falling from a cloud base at a typical altitude under ordinary conditions, the descent takes roughly 2 minutes. 2 minutes of free fall, or rather, 2 minutes of constant velocity falling, since terminal velocity is reached quite quickly and maintained throughout most of the descent. 2 minutes of passing through open air, tumbling slightly, adjusting shape in response to air pressure, carried sideways by whatever wind is present. It is not a long journey in human terms. 2 minutes is less time than it takes to make a cup of tea. But for a drop of water measuring a few millimeters across, it is a substantial passage through space. Smaller drops take longer. A drop at the smaller end of the raindrop size range, falling slowly at perhaps 2 or 3 meters per second, may spend as much as 7 minutes in descent from a standard cloud base altitude. 7 minutes of gentle, slow falling through open air. 7 minutes during which larger, faster drops that formed at the same time and in the same cloud will have already reached the surface and soaked into the ground. The smaller drop is still falling, still making its unhurried way downward through air that offers it significant resistance relative to its modest weight. If we take a specific altitude as a reference point, say, 2,500 feet above the surface, which is a reasonable approximation of a low to moderate cloud base, a raindrop of typical size takes just over 3 minutes to complete the journey. 3 minutes of falling through roughly 760 meters of open atmosphere. Enough time, if you were watching from below and somehow able to track a single drop with your eyes from its departure from the cloud to its arrival at your feet, to witness a journey of genuine duration. From higher cloud bases, 4,000 meters, which is not unusual for convective storm systems, the minimum time for even a large, fast drop is around 7 minutes. A small drop from that altitude might spend 12 or 15 minutes in descent. The cloud that produces a heavy afternoon thunderstorm may have its base several kilometers above the ground. The rain you feel arriving was, in some cases, falling for 10 minutes or more before it touched you. There is something quietly affecting about this when you sit with it. The rain that is falling outside a window right now, if it is raining, began its descent minutes ago. It has been falling while you were reading, or thinking, or settling toward sleep. It left its cloud before this moment, before this particular breath, and has been traveling downward through the atmosphere ever since, indifferent to time, subject only to physics, falling at its unhurried speed toward an arrival it cannot anticipate. The world was different, in small ways, when that rain began to fall. And by the time the last drops of the same storm reach the ground, the world will be different again. Now, there is something the scientists found when they began measuring raindrop velocities in detail, something that, for a phenomenon as apparently simple as a drop of water falling through air, is genuinely strange. Some drops were falling too fast. Not by a dramatic margin. Not at speeds that seemed physically impossible. But by a measurable, consistent amount that exceeded what the established physics predicted they should be doing. Drops exceeding their terminal velocity, moving faster downward than the balance of gravity and drag should allow, were not rare anomalies in the data. When researchers looked carefully at large sets of measured falling drops, more than half of those measured were surpassing the predicted terminal velocity for their size. This is a striking finding. Terminal velocity is not a loose estimate. It is a calculated quantity based on well-understood physics, the drag coefficient of the drop's shape, the density of the air, the mass of the drop, the gravitational acceleration. These are not uncertain numbers. The calculation is solid. And yet real drops, in real air, were consistently outrunning it. The explanation being explored is connected to the turbulent, dynamic nature of the real atmosphere compared to the idealized still air assumed in the standard terminal velocity calculation. In still air, drag builds smoothly and symmetrically as the drop accelerates, and equilibrium is reached cleanly. But the real atmosphere is not still. It is full of small-scale turbulence, gusts, localized variations in air density and movement. A drop falling through a brief downward gust of air experiences temporarily reduced drag. The air around it is moving downward as well, so the relative velocity between the drop and the air is lower, drag is reduced, and the drop accelerates beyond the speed it would maintain in truly still air. These brief accelerations may not last long, and may be followed by moments of increased drag as the drop encounters upward moving air. But if measurements are taken at a particular moment when the drop happens to be in a downward gust, the recorded speed will exceed the still air terminal velocity. When this happens consistently for more than half of all measured drops, it tells us something important. The standard model of raindrop terminal velocity, while accurate on average and in principle, is describing a somewhat idealized drop in a somewhat idealized atmosphere. Real rain falls through a real, turbulent, uneven atmosphere, and its behavior reflects that complexity. The atmosphere is never the simple, smooth, uniform medium that equations assume. It breathes. It gusts and eddies and swirls at scales ranging from the microscopic to the continental. Every drop that falls through it is subject to that variability, sped up here, slowed there, pushed sideways by one current and deflected by another. The fall is never quite as the model predicts because the model cannot capture every detail of a living, moving atmosphere. And perhaps that is fitting. Rain is not a laboratory phenomenon. It is a product of one of the most complex physical systems on Earth, the atmosphere, and it retains some of that complexity even in the behavior of individual drops. The science describes it well, but it does not describe it completely. There is always a small residual wildness in the data, a reminder that nature operates at a level of detail that exceeds any model we build to contain it. Every drop falls on its own terms, through its own small portion of atmosphere, at its own speed, shaped by all the forces and disturbances it encounters along the way. And it arrives exactly when and where those forces bring it. The finding that more than half of measured raindrops exceed their predicted terminal velocity was striking enough on its own. But as researchers continued to gather data, the picture that emerged was more specific, and in some ways more surprising, than the initial discovery suggested. The excess speed was not distributed evenly across all drop sizes. It was concentrated at the smaller end of the spectrum, and at that end, the departures from predicted velocity were not modest. They were, in some cases, extraordinary. Small drops, those in the lower range of raindrop dimensions, were recorded falling at speeds 30 to 60% faster than their calculated terminal velocities. Not a few percent over. Not a marginal excess that might be explained away by measurement uncertainty. 30 to 60%. A drop predicted to fall at 2 meters per second arriving at nearly 3 meters per second. A drop expected to reach the surface in 7 minutes arriving in 4 or 5. The gap between prediction and measurement was, at this scale, genuinely large. And it went further still. Some tiny drops, the very smallest in the rain spectrum, barely qualifying as drops rather than large drizzle, were recorded falling at speeds up to 10 times faster than their predicted terminal velocity. 10 times. A drop that still air physics would expect to drift down at half a meter per second was instead falling at 5 meters per second, approaching the speed of drops many times its size. If you were designing an experiment specifically to produce a counterintuitive result, it would be difficult to engineer one more surprising than this. The pattern across the data is consistent. Smaller drops show larger proportional departures from predicted terminal velocity than larger drops do. The effect is real, it is measurable, and it scales with size in a specific direction. 30% of small drops in the studies exceed their expected speed by a meaningful margin, not occasionally, not under unusual conditions, but as a regular feature of how small drops behave in real rainfall. The average excess speed across the full population of small drops sitting above their predicted terminal velocity comes to around 30%. 30% faster than theory predicts, as a typical finding, not an extreme case. This is a systematic effect, not a statistical fluctuation. Something interesting also emerges when the data is broken down by rainfall intensity. In heavy rain, the kind produced by strong convective storms, with large drops and high rainfall rates, there is a tendency for clusters of fast-moving small drops to appear together. The speedy drops are not evenly distributed throughout the rainfall. They arrive in groups, in waves, concentrated in particular parts of the storm's output. This clustering is a clue, and it points toward what is probably the most important explanation for the entire phenomenon. The explanation begins with large drops breaking apart. A study involving 64,000 measured drops, a dataset large enough to reveal statistical patterns that smaller samples would miss, confirmed and strengthened the findings that earlier, smaller studies had suggested. The behavior was consistent across the full dataset. Small drops were regularly faster than predicted. The effect was concentrated at smaller sizes. And the clustering in heavy rain aligned with what would be expected if the fast small drops were being produced not by independent condensation and growth, but by the fragmentation of larger drops. Here is what happens. A large drop, one approaching the upper limit of stability, perhaps 4 or 5 or 6 millimeters in diameter, falls at close to its terminal velocity, which for a drop of that size is around 9 or 10 meters per second. As it falls, it becomes increasingly unstable. The forces working against its integrity, air pressure on its flattened base, the inertia of its own mass, the turbulence of its environment, eventually overcome the surface tension holding it together. The drop breaks apart. The fragments created by this breakup are smaller drops. Some are medium-sized, some are quite small. And here is the crucial point. In the first moments after breakup, these fragments are still moving at roughly the speed of the parent drop. They have inherited its momentum. A fragment 1 millimeter in diameter, which under normal circumstances would have a terminal velocity of perhaps 3 or 4 meters per second, has just been released at 9 or 10 meters per second, 2 or 3 times its own terminal velocity. The fragment has not yet had time to decelerate to its own equilibrium speed. The drag acting on it will eventually slow it down. But drag takes time to do its work. In the seconds immediately after breakup, the small fragment is simply moving fast, faster than it has any right to, by the standard prediction, because it is carrying the speed of something much larger that no longer exists. If the fragment is measured during this period, before it has had time to decelerate to its own terminal velocity, it will appear to be exceeding its predicted speed dramatically. And if it falls only a short distance after breakup before being measured, it may arrive at the measurement point still carrying much of the parent drop's speed. This inheritance of speed from parent to fragment explains why the effect is so strongly concentrated in small drops, why it is more pronounced in heavy rain where large drops are more common and breakup events are more frequent, and why fast small drops tend to cluster together. A single large drop breaking apart produces multiple fast fragments simultaneously. Those fragments arrive at the measurement level around the same time, appearing as a cluster of anomalously fast small drops. In heavy rain, where breakup events are happening constantly throughout the storm, these clusters overlap and reinforce each other, creating a population of small drops that is, collectively, moving much faster than a naive application of terminal velocity theory would predict. The deeper implication of all this is both subtle and important. In the real atmosphere, at any given moment during active rainfall, small drops may be outrunning larger ones. A fragment released at high speed from a fragmenting large drop can, for a period of time, be falling faster than a medium-sized drop that has been descending steadily from the cloud base at its own equilibrium speed. The orderly picture in which larger drops always fall faster and arrive first is, under real-world conditions with active breakup occurring throughout the storm, regularly violated. Rain is not a well-organized procession. It is a constantly churning, fragmenting, recombining cascade in which the speeds of individual drops depend not just on their size but on their recent history, on whether they arrived at their current size through gradual growth from a cloud droplet or through sudden liberation from a larger drop that just came apart. A 64,000 drop study is not a small dataset. It represents a serious, methodical attempt to characterize the behavior of real rainfall rather than idealized rainfall, and its confirmation of these anomalous speeds elevated what might have been a curious footnote into something with genuine implications for how precipitation is modeled and understood. Weather forecasting, rainfall erosion models, radar interpretation of precipitation intensity, the calibration of rain gauges, all of these depend, at some level, on assumptions about how fast drops of different sizes fall. If those assumptions are systematically wrong for small drops, the downstream effects ripple through every system that relies on them. The 30% average excess speed for small drops is not a trivial correction. It is a meaningful revision to a foundational assumption, and the science of precipitation is still working through its full implications. There is something almost philosophical about what these findings describe. We build models to capture the behavior of the natural world, and the models work well in smooth, idealized conditions. They predict terminal velocities from first principles, and the predictions are, in general, correct. But the real world does not operate in smooth, idealized conditions. It operates in turbulence and complexity, with large drops fragmenting and releasing their speed to their offspring, with gusts accelerating drops through brief windows of reduced drag, with the inheritance of momentum blurring the clean relationship between size and speed. The atmosphere is not a controlled experiment. It is a living system, full of processes that interact with one another in ways that no single equation fully captures. Every drop that falls through it is subject to that complexity. Every drop carries the legacy of whatever happened to it on the way down, the turbulence it encountered, the collision that made it, or the fragmentation that released it from something larger. Rain is simpler than almost anything else you can think about before sleep. It falls. It is water. It comes from clouds. These are things known to every child in every culture that has ever existed. And yet, the closer you look at it, the more it reveals. Layer after layer of unexpected behavior, careful measurement, revised understanding. A science that has been studied for more than a century and is still, in the details of individual falling drops, producing results that surprise the people who study it. The water outside, or the memory of water falling on a quiet roof, or the imagined sound of rain on a nighttime window, all of it is this. All of it is drops with histories, carrying inherited speeds, negotiating with the air, arriving in their own time and at their own pace. Falling as they have always fallen. As they will always fall. Quietly. Continuously. Without pause. There is a certain point in any scientific investigation where the accumulating weight of anomalous data demands something more than a minor adjustment to existing models. The findings around raindrop terminal velocity, the consistent excess speeds, the dramatic departures at small drop sizes, the 10 times overperformance of the tiniest drops, the confirmation across 64,000 measured examples, may be approaching that point. The breakup inheritance explanation accounts for much of what is observed. Large drops fragment and release fast-moving smaller drops that have not yet decelerated to their own equilibrium speeds. This is real, it is physically sensible, and it explains the clustering of fast small drops in heavy rain with convincing coherence. But whether it accounts for all of the anomalous behavior across all conditions is a question the science has not yet fully settled. There are cases, drops measured in light rain where large drop fragmentation is less frequent, drops that appear to be moving fast despite no obvious parent drop to inherit speed from, where the explanation feels incomplete. This is where the science currently sits. Not in confusion, but in the productive state of having a good partial explanation and an honest acknowledgement that the full picture has not yet been assembled. New measurement techniques, better high-speed imaging, more sophisticated atmospheric sampling, these are being brought to bear on the question. The answers, when they come, will refine not just our understanding of terminal velocity but our understanding of how precipitation behaves across its full range of conditions. The practical stakes are not trivial. Every rainfall measurement made by a rain gauge, every estimate of precipitation intensity derived from weather radar, every model that predicts how much water is falling on a watershed or a catchment area, all of these depend on assumptions about drop size and fall speed. Radar in particular estimates rainfall rates by measuring the intensity of reflected signals from falling drops, and the relationship between signal strength and actual rainfall amount depends on assumed drop sizes and their associated fall speeds. If small drops are systematically falling faster than assumed, the radar is, in effect, undercounting the water in light rain while potentially miscounting the contribution of small drops in heavy rain. For applications like flood forecasting, agricultural water budgeting, and reservoir management, these are not abstract errors. They translate into real discrepancies between predicted and actual water delivery to the surface. The scientists studying anomalous raindrop speeds are not engaged in purely academic work. They are refining the foundational measurements that real-world water management depends on. But even as the science works toward a more complete understanding, the drops themselves continue falling, indifferent to measurement and modeling. They approach the surface with the same physics they have always had, the same quiet negotiation between gravity and air, the same inheritance of speed from whatever came before them. And as they descend through the final hundreds of meters toward the ground, something changes. The air grows denser and moister closer to the surface. The lower atmosphere, particularly in humid conditions, contains more water vapor and more fine droplets than the clearer air higher up. A descending raindrop, still growing through collision in the cloud, may continue to collect moisture during its descent through this lower layer. The process that built it from a dust particle to a millimeter-sized drop in the cloud does not stop abruptly at the cloud base. It continues, more slowly, as the drop passes through the haze and humidity of the lowest atmospheric layers. This continued collection is modest in most cases. The drop has already done most of its growing. But it is a reminder that the boundary between cloud and clear air is not as sharp or as final as it might appear from below. The cloud grades into mist, the mist grades into humid air, and the drop continues interacting with its environment all the way down. A raindrop from a typical cloud base at moderate altitude spends only a few minutes in this final descent. 2 minutes, 3 minutes, perhaps 7 for the smallest drops from the highest bases. In human terms, this is brief. In the context of the full water cycle, the thousands of years a water molecule might spend locked in a glacier, the centuries it might rest in a deep aquifer, the months it might travel through an ocean current, a few minutes of freefall is barely a moment. It is the last, brief, visible chapter of a journey that may have been unfolding for longer than recorded human civilization. And then it arrives. The relationship between rain and the Earth's surface is ancient and complex and, for living things, utterly fundamental. Rain is not simply water delivered to a location. It is a force that acts on the world it strikes, reshaping landscapes over geological time, sustaining life in the immediate term, and carrying within it both the gifts and the challenges that have shaped human existence since the beginning. There is joy in rain. Cultures in every part of the world that depends on seasonal rainfall understand this in a visceral, uncomplicated way. The arrival of rain after a dry period is not merely a meteorological event. It is relief. It is the continuation of life. Farmers watching a long-awaited storm arrive over dry fields experience something that no amount of irrigation infrastructure entirely replaces: the particular reassurance of water falling freely from the sky, of the world being replenished by something that requires no human effort to produce. But rain is also force. A heavy raindrop, one of the large, fast drops produced by a strong convective storm, arrives at the surface with meaningful kinetic energy, and it does not spend that energy gently. When a large drop strikes bare, unprotected soil, it explodes on impact. The drop flattens and splashes outward at high speed, dislodging soil particles from the surface with a force that seems disproportionate to the size of the drop. This is the beginning of rainfall erosion, one of the most significant geological forces shaping the Earth's surface over time. Compaction happens as well. Repeated raindrop impacts on soil seal the surface, breaking down the fine structure of the topmost layer and reducing its ability to absorb water. Compacted soil repels water rather than accepting it, increasing runoff, reducing infiltration, concentrating rainfall into surface flows that carry soil particles away. The same rain that sustains plant life can, on bare or vulnerable soils, degrade the very ground it falls on. Agriculture has grappled with this tension for as long as humans have been farming. But most rain does not fall on bare soil. It falls on leaves. The leaf is one of the most important surfaces in the water cycle, and it interacts with rain in ways that are often underappreciated. When a raindrop strikes a leaf, several things can happen. The drop may be absorbed into a thin film of water on the leaf's surface. It may roll along the leaf's curve and drip off the edge. It may be caught in a pocket formed by the leaf's shape, held there until it evaporates back into the air or runs down the stem. On large, waxy leaves, it may beat into a perfect sphere and roll off cleanly, the leaf's surface chemistry shedding water almost completely. In a forest, the canopy intercepts a significant fraction of rainfall before it ever reaches the ground. Some of that intercepted water evaporates directly from leaf surfaces without ever touching the soil. The rest drips off leaves and branches in altered form, concentrated into larger drops by the collecting action of leaf edges, delayed in its arrival at the ground by the time it spends moving through the canopy. Rainfall that has passed through a forest canopy is different in timing, drop size, and spatial distribution from rainfall that falls on open ground. The forest mediates the rain, slows it, redistributes it, and returns some of it to the atmosphere before it even begins its surface journey. For a drop that does reach the ground, the range of possible next chapters is enormous. It may fall on a slope and begin moving immediately downhill, joining other drops in a thin sheet of surface flow, eventually finding a channel, then a stream, then a river. It may travel hundreds or thousands of kilometers through the river system before reaching the ocean, its journey at the surface lasting days or weeks, passing through landscapes of extraordinary variety before returning to the vast water body from which, in some earlier cycle, it once evaporated. It may soak into the ground. This is the quiet fate of a large proportion of all rain that falls, and it is one of the most important things rain does. Water infiltrating soil moves downward under gravity, passing through the spaces between soil particles, entering the zone where rock and sediment are saturated with water. This is groundwater, one of the planet's most vital and least visible resources. Aquifers hold enormous quantities of water accumulated over thousands of years of slow infiltration. The water in a deep well may have fallen as rain during a different climate, in a different era, filtered through layers of rock over centuries before arriving at the depth from which it is now drawn. Every raindrop that soaks into permeable ground is making a contribution to a reserve that may sustain life in ways and at times it cannot anticipate. The same drop of water that arrives at the surface as rain may, within minutes, be evaporating again from a sun-warmed pavement. Or it may spend 1,000 years in an aquifer before emerging in a spring. The range of possible journeys from a single point of surface contact is essentially infinite, determined by the particular conditions of the place and moment where the drop lands. This extraordinary variability of outcome from a single point of arrival is part of what makes the water cycle so difficult to fully comprehend and so endlessly fascinating to explore. Somewhere on Earth right now, rain is falling with a particular intensity and in a particular volume that no other place on the planet experiences. Mawsynram, a village in the Meghalaya region of northeastern India, holds the distinction of being the wettest place on Earth by average annual rainfall. The numbers associated with this place are almost incomprehensible in their scale. Rainfall there is driven by monsoon moisture moving north from the Bay of Bengal and striking the hills of Meghalaya, which means abode of clouds in Sanskrit, a name that turns out to be entirely literal. The rainfall is not merely heavy. It is sustained, relentless, a feature of the landscape as fundamental as the hills themselves. The people of Mawsynram have adapted their lives and their architecture to water in quantities that residents of drier places can barely imagine. Contrast that with Wales, in the western part of Britain, a place widely regarded by its own residents as notably rainy, a place where gray skies and drizzle are cultural touchstones, where rain gear is a practical necessity rather than a precaution. Wales receives a fraction of Mawsynram's annual rainfall. What feels like relentless rain in one of Europe's wetter regions is, by the standards of the world's truly wet places, genuinely modest. Perception of rainfall is profoundly relative. The rain that makes a Welsh autumn feel saturated would barely register in Meghalaya. At the other extreme, Antarctica is the driest continent on Earth. This surprises many people. Antarctica is covered in ice, and ice is frozen water, so it seems contradictory that a place surrounded by so much frozen water should qualify as a desert. But the classification of a desert is based not on how much water is present but on how little precipitation falls. In Antarctica's interior, annual precipitation is so low, much of it falling as snow, and very little of it at that by any meteorological definition, it qualifies as a polar desert. The ice that covers it is ancient, accumulated over hundreds of thousands of years of slow accumulation. The rate of new precipitation is extremely low. Water is everywhere in Antarctica, but it is almost entirely historical water, locked away from the active cycle. And if the range of rainfall conditions on Earth is extraordinary, the range of what passes for precipitation across the solar system is stranger still. On Venus, models suggest that sulfuric acid droplets form in the upper atmosphere and descend, but the planet's surface is so hot that they evaporate long before reaching the ground. Rain that never arrives. Precipitation that exists only in the sky, cycling endlessly between condensation and evaporation in a thick, crushing atmosphere. On Titan, Saturn's largest moon, methane plays the role that water plays on Earth. There are methane clouds, methane rain, methane rivers, and lakes and seas. The water cycle has an analog on Titan, but the substance cycling is not water, it is a hydrocarbon, liquid at Titan's extraordinary cold temperatures, following the same evaporation condensation precipitation logic that water follows on Earth, but in a chemistry utterly unlike our own. On exoplanets even further from familiar conditions, Theoretical models suggest rain of liquid iron, of glass, of silicates condensed from superheated atmospheric vapor. Worlds where the sky rains molten rock. Worlds where the precipitation is made of substances that exist as gas at any temperature a human being could survive. The same physics, gravity pulling condensed material downward through an atmosphere, playing out in materials and conditions that bear no resemblance to a quiet Earth evening with water falling softly on a roof. Rain, as a physical process, is not unique to Earth. It is a consequence of basic physics that will occur on any world with an atmosphere and a substance that can cycle between gas and liquid at that world's temperatures and pressures. What is unique to Earth is water. What is unique to Earth is this particular substance, with its extraordinary properties, its high surface tension, its unusual density relationship between liquid and solid, its capacity to dissolve almost anything, cycling through this particular system, sustaining this particular kind of life. For as long as there have been humans, rain has been more than a physical event. Every agricultural civilization that has ever existed has depended on rainfall for its survival, and that dependence has generated an enormous diversity of cultural responses, rituals, prayers, dances, offerings, festivals, and deep bodies of spiritual and poetic meaning built around the arrival or absence of rain. The rain dances of indigenous peoples of the American Southwest were not naive attempts to control the weather. They were sophisticated expressions of a community's relationship with water, acknowledgments of dependency, affirmations of hope, communal practices that bound people together in shared attention to the most essential variable in their agricultural lives. The monsoon festivals of South Asia, the prayers for rain preserved in ancient texts from Mesopotamia and Egypt and Israel, the rain deities found in virtually every pantheon from every era of human religious history, all of them are evidence of how deeply the relationship between humans and rainfall is woven into the fabric of culture and consciousness. We are not the first people to lie quietly listening to rain and feel something that goes beyond mere awareness of weather. We are participants in a response that goes back to the beginning of human experience, the response of a creature that needs water to live, hearing it arrive from the sky, and feeling, beneath whatever thoughts are present in the mind, something older than language. Something close to gratitude. And now the cycle completes itself. The drop that fell, wherever it landed, on leaf or soil or stone or water, does not stay. It never stays for long. If it landed on a sun-warmed surface, evaporation may begin within hours. The sun's energy loosens the molecular bonds holding it in liquid form, and water molecules begin to lift away from the surface one by one, rising into the air as vapor. Invisible again. Weightless again. Beginning once more the ascent into the atmosphere that started this journey. If it's soaked into the ground, it may spend years, decades, centuries, moving slowly through rock and sediment before it emerges in a spring, enters a stream, reaches the ocean, and evaporates from the ocean's surface to begin again. If it fell on ice, it may be locked away for millennia, preserved in a glacier or an ice sheet, moving imperceptibly downslope over centuries, eventually reaching the sea as meltwater. However long it takes, however many detours the journey includes, water never truly disappears. It transforms. It moves. It changes state and location and temperature and salinity and form. But it remains. The same water, cycling through the same system, governed by the same physics, driven by the same sun. The journey of a raindrop is not a journey with a clear beginning or end. It is a segment of something continuous, a single visible episode in a story that has been running without interruption for 4 billion years. The water that fell on you the last time you stood in rain carries a history that stretches back before your great-great-grandparents were born, before the country you live in existed, before the language you think in had taken its current form. It may have been ocean water in the Pacific, groundwater in an aquifer beneath a continent, snowpack on a mountain range that no longer exists. It may have passed through the body of an animal, through the roots of a tree, through a cloud over a place you have never been. And it is almost impossible to resist the thought, one that science does not contradict, that some portion of the water that has ever touched your life was present on this planet when enormous creatures moved through forests and shallows, breathing and drinking and living under a sky that looked, from a distance, very much like this one. The same water. Not the same in the sense of metaphor, but the same in the literal sense. The same molecules. Passed from that world to this one through an unbroken chain of cycling and returning, over spans of time that dwarf everything human civilization has ever built or dreamed. And it will continue. Long after tonight, long after all of this, the water cycle will still be running. The same drops, changed in location and form, unchanged in substance, will still be rising from warm water surfaces, still gathering around dust particles in cold air, still forming clouds and falling as rain in some other place, on some other surface, under some other sky. Perhaps the water that has settled somewhere near you tonight, in the air, in the ground, in the quiet of a glass on a nightstand, will someday fall as rain in a place that does not yet have a name. In a landscape we cannot imagine. On a day that has not yet been numbered. Falling then as it has always fallen. Softly. Continuously. Without end.